6.7 magnetic field produced by a current. So as we know that, kalau yang first awal tu, kita pakai our right hand grip rule. Kita genggam wire, ikut arah current, our thumb ikut arah current, then there will be magnetic field produced around the wire. Same goes to this concept, magnetic field produced by a current. Okay, this one we can determine by using the Biot-Savart law. For example, yang garis line ni adalah wire. Current flow through it, there will be magnetic field around this wire. So this is Biot-Savart law, the general equation for Biot-Savart law. But since we are going to learn on 3 different shapes, which is long straight wire, circular loop dan juga solenoid, so dia dah applykan siap-siap shape into this Biot-Savart law. So you don't have to integrate apa-apa, tak perlu. You just need to focus on the equation for each shape lah. Using Biot-Savart law to find the magnitude of the magnetic field around a long straight wire, so the equation is B, magnetic field strength, equal to mu naught, which is the permeability constant of free space, okay, times with the I, current that flow through the wire, divided with 2 pi r. R is the distance of the point from the wire. So what does it mean, distance the point from the wire? Let's say we have a wire and then there is magnetic field around that wire. So kalau saya tanya berapakah magnetic field strength dekat 2 cm daripada wire tersebut, 2 cm itulah dia punya R. Okay, meanwhile for the permeability constant, the value is constant, which is 4 pi times 10 to the power of -7 Henry per meter. So make sure you know how to use this equation, this value. Maybe you can solve for 4 pi dulu, baru use 10 kuasa -7 kan dia. Okay. From the expression, B is proportional to the current flowing through the conductor and inversely proportional to the distance from the conductor. So let's say this is the wire. This is pandangan hadapan and this is pandangan atas. So biasanya kita tengok pandangan atas lah. So as we view it from above, current will flow out of the page macam ni. So we use our right hand grip rule. So the magnetic field will be directed anti-clockwise. Okay. So if I ask you to find the magnetic field strength at this point, so you need to find B by using this equation. And then the direction we can determine by, sebab dia mesti tangential to the center. So kalau let's say you cari B dekat point ni, dia punya direction will be upward. Kalau you cari B dekat point sini, direction B dia akan downwards. Okay. So B is proportional dengan current. So bila current meningkat, lagi banyak magnetic field yang boleh dihasilkan. And when if the R meningkat, maksudnya kalau R meningkat lagi jauh, so magnetic field akan berkurang. Kalau R kita dekat point ni, dekat dengan center ni, maka dia punya B increases lah, makin meningkat. So you need to understand juga lah dia punya equation, dia punya proportionality ni. Alright, so direction B always tangential to that point. So in this one, the example if the current flows downward, so as we view it from above, we will see it like this. The current will flow into the page and it will mix clockwise motion. So if we find the magnetic field strength dekat point ni, okay, we can use the equation and then direction datang ke bawah. Okay. Second one is magnetic field at the center of a circular loop. By using Biot-Savart law, the equation is B equal to mu naught I over 2R. So mu naught is the permeability constant, 4 pi times 10 to the power of -7 Henry per meter. I is the current flow on the loop. 2 is number 2. R is the, what is mean by R is the radius of circular loop. Okay, circular loop ni bentuk bulatan lah, wire yang bentuk bulatan. So kalau single wire, satu wire saja, disedaratkan dengan 1. Kalau ada 10 wire bulatan tu, disedaratkan dengan N lah, sedaratkan dengan 10. So dua ni ialah equation sama, it just that berapa banyak bilangan loop ataupun turns of the loop tu, you just daratkan lah. Okay. And then the third one is magnetic field inside a solenoid. Okay, dalam solenoid bukan kat luar solenoid. So the equation is B equal to mu naught Ni over L. Mu naught is the permeability constant, N is the number of turns on the solenoid, I is the current flow, L is the length of the solenoid, panjang solenoid dari hujung ke hujung. And then from this equation, kita ada satu equation ratio lah, N per L, which is sama juga dengan small letter n ni. So, solenoid ni kan let's say dia panjang, dia ada banyak turns. So, kalau you nak cari magnetic field dekat hujung solenoid tu, so you kena gunakan equation ni, carilah dia punya B dulu ataupun nanti you bahagikan 2 ataupun you gunakan equation ni. Okay, sebab apa? Equation tadi adalah untuk magnetic field dekat center of the solenoid, tengah-tengah dalam solenoid tu, bukan ke ujung. Sebab kalau ke ujung, dia dah lain. Okay, so kalau ke ujung bahagi 2, kalau ada kita masukkan iron core into the solenoid, we need to times it with the permeability of that iron core. Okay, so nilai ni akan bagilah. Okay, so let's see the example 6.8. Two long straight parallel wire are separated at a distance of 5 cm. Each carries a current of 25 ampere. Determine the magnitude and direction of the resultant magnetic field strength produced between the wires at a point 2 cm from one of the wire and 3 cm from the other wire if the currents flow same direction and opposite direction. So why not we sketch the diagram first. So based on the equation, we will have this diagram. We have two parallel straight wire. The distance between them is 0.05 cm. And then we want to find the magnetic field strength. Okay, dekat jarak ni 2 cm dan juga 3 cm daripada wire tu. If the current flows same direction, so arah current sama. Okay, so what we do is, when you have sketch this diagram to show that you understand the equation, kita akan tengok daripada pandangan atas. So from the upper view, this is wire 1, so the current is flow out of the page. Wire 2 out of the page also. So by using our right hand grip rule, we grip the wire, then we will see that the magnetic field produced is anti-clockwise. This one also anti-clockwise. So dia punya resultant magnetic field strength dihasilkan adalah macam ni. Okay, kenapa kat tengah-tengah ni kosong? Sebab dia cancel out each other. Okay, so now kita nak cari magnetic field strength 2 cm daripada wire 1 and 3 cm daripada wire 2. So berapakah resultant magnetic field strength here? Kenapa dipanggil resultant? Sebab akan ada B1 iaitu magnetic field yang dihasilkan daripada wire 1 dan akan ada B2 magnetic field yang dihasilkan daripada wire 2. So bila ada 2 B, kita kena nak cari resultant dia. Alright, so how to find B1, how to find B2? We use the equation B equal to mu naught I over 2 pi r. So, mu naught is permeability constant for pi times 10 to the power 97. I is the current that flow through each wire. 2 pi r. R adalah jarak point tersebut daripada setiap wire. So, kalau untuk B1 ni, R dia adalah 0.02 meter. Kalau untuk B2, R dia adalah 0.03 meter. So, kita cari B1, kita cari B2. So, when you get B1, ni baru magnitude. To find the punya direction is from our sketch lah tadi. Okay, let's say you nak cari direction B1. So, you tengok kan dia anti-clockwise. So, at this point, the direction of the magnetic field is upward. Dekat point ni sahaja ya, dia akan ke atas. So, direction upward. For B2, dia anti-clockwise. Dekat point ni, dia akan ke bawah. So, dia ada dua cara lah nak cari resultant ni. Kalau satu ke atas, satu ke bawah. Kita gunakan konsep resultant vector. Sama ada you nak tambahkan dua-dua. Kalau yang ke bawah akan jadi negatif. Jadilah, inilah jawapan dia. 8.3 times 10 to the power negative 5 Tesla. Ataupun kalau you nak kata yang ke atas positif, yang ke bawah negatif pun boleh juga. Tak ada masalah. So, bila you dapat jawapan resultant you 8.3 which is positive value, the resultant direction is upward. For question B, since the direction of current will be opposite, okay, so let's say kita kata satu ke atas, satu ke bawah. So from the upper view, we will see that wire 1, current 1 is out of the page, wire 2 is into the page. So, the direction of B1 at this point is upward. Direction of B2 at 3 cm from wire 2 is upward also. So kita cari nilai B1, kita cari nilai B2. Since dua-dua tadi arah dekat atas, so kita tambahkan sahaja. Dapatlah 4.17 times 10 to the power of -4 Tesla. Example 6.9. Radius of a circular loop is 0.5 meter and carries a current of 10 ampere. Calculate the magnitude of the magnetic field strength at the center of the loop and determine its direction. So we have this circular loop. Radius dia 0.5 cm and carries current 10 ampere. Kita nak cari B at the center of the loop. So biot sahabat law said that the equation is B equal to mu naught I over 2R. So mu naught is 4 pi times 10 to the power of 97. R is 10 ampere. 2 times with R radius 0.5. So we will get the equation. The answer is 1.26 times 10 to the power of 95 Tesla. For the direction, cara kita nak tahu direction dia ke mana. So you kena grip the circular loop lah dekat semua bahagian. You akan nampak at this point, center of the loop ni, magnetic field semua masuk ke dalam page. Okay, so that's why dia tulis kat sini lah, direction is into the page. Example 6.10. A copper wire of length 80 meter is coiled and becomes a solenoid with diameter 10 cm and length 1 meter. If the current of 1.2 ampere flows through the wire, calculate the magnetic field strength if the solenoid is placed in air, the soft iron core is inserted into the solenoid. So make sure you cari keyword of this equation. Apa soalan nak sebenarnya? We need to find the magnetic field strength, which is B, and the shape of the wire is solenoid. So by using biot sahabat law to find the magnetic field strength at the center of the solenoid, we use the equation B equal to mu naught n I over L. Alright, so mu naught is 4 pi times 10 to the power of -7. N, the number of turns. So number of turns is not given in this equation. I, current, is 1.2 ampere. So the length is 1 meter. So to find the number of turns in this coil or in this solenoid, we need to use the information given, which is diameter, length 80 meter, and also the length of the solenoid. So to find the diameter, to find the number of turns, we need to find the circumference of the coil. Okay, so circumference of a circle is 2 pi r. We can substitute the value of r right here, which is diameter bagi 2, we get 0.05. Then the circumference of the circle is 0.314 meter. From this circumference, we can find the number of turns by using number of turns equal to the total length divided with circumference. Then we will get 254.65 turns. Kita akan ambil nilai nombor bulat sahaja, which is 2.4 turns, to substitute into this equation. Then since there is no iron core inserted into this coil, maksudnya kat sini adalah air sahaja. So we substitute this one is S1, and then mu naught, the number of turns, current, and the length of the coil of the solenoid from here to here, which is 1 meter. Then we will get the magnetic field at the center of the solenoid, which is 3.83 times 10 to the power of -4 Tesla. For question B, since there is iron core inserted in between inside this solenoid, so nilai jawapan tadi kita boleh darabkan sahaja dengan 370, ataupun we can find it again by using the same equation. Then you will get 0.14 Tesla. So apa function kita masukkan iron core dalam solenoid is to increase the magnetic field produced. So prove by the equation, by the calculation, we'll get the magnetic field for this situation is greater compared to the first situation just now.